Hello everyone, this is Universum, the place where you learn about the entire universe, how it began, and how it will end. In this video, we're going to be talking about bra and ket notation as explained in multi-dimensional spaces such as in a Hilbert space, for example. So the first thing that we need to explain is, well, what the heck is a bra and ket? I know it sounds a bit funny, but anyways, so bra and ket notation, what it is, so it's representing two eigenvectors. Two eigenvector values that are diverging in different ways. They're perpendicular to one another. Ultimately, what you're trying to do is you're trying to write an inner product of two separate basis vectors hit upon a bra or a ket. A bra looks like a slanted line with a straight line, and then a ket just looks like the exact opposite of that. Really simple stuff. Ultimately, we're trying to plug in is like you're trying to plug in a vector space. You're trying to find out the divergence, convergence, or etc. You're trying to find any of those. Now, many bra and ket notation equations can get a bit complex at times. Like, for instance, an example of one would be the ket notation of phi, which then would be multiplied by the bra, which then will be hit upon the bra notation of psi, which then will be equal to the matrix component of psi 1, psi 2, etc., 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 on and on, which is usually when you see in linear algebra or calculus, ... which then that's going to be equal to the sum of phi n, and usually this means an undefined vector value, which then that's going to be multiplied by the time-independent value of phi 1, phi 2, well, phi star 1, sorry about that. And then that is going to be, of course, ... because it goes on forever, which then that is going to be equal to the sum of phi star n, which then is going to be equal to a complex matrix, which consists of both components such as phi and psi. If you would like to know it, then hold on to your horses. So what it is that it is phi sub 1 multiplied by psi sub 1 star, which then that is going to be multiplied by a matrix net notation or something. Now I'm not going to say that every single time, okay? So I'm just going to say that once every single time there's another notation. Just expect me to say, don't expect me to say that, okay? And then that's going to be multiplied by psi sub 1 multiplied by, sorry, I got them mixed up. Phi sub 1 multiplied by psi star sub 1. So psi star is usually known as the wave function and the Dirac delta function. Well, not necessarily delta function, but in the Dirac notation. Then that's going to be ... yet again, which then that is going to be multiplied, well, of course, as I said in the first one, just remember that, which then that is going to be equal to the sum of phi sub 1 multiplied by time-independent factor of psi star sub n, which then that is going to be a lower product value, which then, now if you're wondering what lower product means, it simply just means different values in the matrix computation value. So then there is going to be phi sub 2, and just letting you know, I'm not really going to explain the rest of it, just letting you know, it's expected to just keep on going on and on and on in the matrix. And that's what a matrix means. It means a value that can just keep on going, and you're going to need to decipher the matrix. And then, all in all the values always end up equaling phi sub n multiplied by psi sub n. So now that we got the bra and ket notation out of the way, which was lovely made by good old Paul Dirac over there. Well, there's nothing in this room, but you get what I mean. Anyway, so Paul Dirac, he was a brilliant physicist who worked in many, many fields. Most of it was quantum mechanics. And he worked at CERN. CERN being one of the most brilliant quantum mechanical institutions of all time. Now with all those matrices they saw over there, as explained in Dirac notation and bra and ket notation, it can get a bit complex at times, like all these finite values, boundary conditions, trying to find the expectation value of a certain type of vector. It all can get a bit overwhelming sometimes. But don't worry, I can help you on this journey of quantum mechanics. So now staying on the topic of matrices, we get into these things that's called Pauling matrices, which was made by a lovely another physicist called Wolfgang Pauli. Man, what a name, Wolfgang Pauli. Anyways, so Pauli matrices, ultimately they are trying to define different values of sigma at certain different points in a vector field. Now, if you have been in some calculus courses, you may know that you can easily define a vector field by many different theorems, one of which being Green's theorem. Now, Green's theorem is mostly used for surface, but it can be used for some types of vector fields. Not all types, but some types. So then Pauli matrices, some of them can consist of sigma sub x. X usually is a undefined vector value, which means that's going to be equal to a vector, which simply is going to be an undefined vector with 2 zeros diagonal to one another and 2 ones opposite diagonal to one another, which then is going to be multiplied, or star, whatever the heck you want to do, which then that's going to be multiplied by another yet sigma, which then is going to be to the y value. Ultimately, you can represent this by integral, in case you are wondering. But not all types of Pauli matrices, which then the sigma is going to be equal to 0, negative I being a complex number fluent throughout the equation, which then orthogonal to it is going to be positive I. And then what is going to be next is that then there is going to be 0 that's going to be diagonal to the 0, which then what's going to be happening next is you'll be doing the exact same thing that you did in the first one, except reversed, and there will be 1, negative 1. And then of course there's some different types of algebraic properties of it. Ultimately, the algebraic properties are multiplying different values of sigma by one another, different values just overlapping until basically you get a matrix. And in the end, all these matrices usually end up equaling capital I. Usually, at least. Like, for instance, if you use triple vectors, like, for instance, x, y, z, sigma squared, which then is going to be equal to the negative imaginary component, actually, of sigma, 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 and, of course, sub x, y, z, of course, which then is going to be equal to 1, 0, and then 0, 1, of course, as explained in the first sigma one, which then is going to be equal to capital I, as I just explained a few seconds ago. Which then, what you're going to do is you're going to need to do a function, which is usually defined as det, which then is going to be the time-independent value of sigma sub I, which then is going to be equal to negative 1. The reason being behind this is that, this can include every single type of value that you can, possibly comprehend of all the x, y, and z components of this. And what you can do is that you can make that the sum of negative 1, which then you're going to do a TR value, which then this TR value, which is going to be multiplied by yet again another sigma to the I value, which then that is going to be equal to 0. Now the reason being behind this, because Wilson's usually trig functions usually are a bit interesting sometimes. Sometimes they can just... Sorry, I'm not explaining it very well, am I? Sorry. Now, in the end, ultimately, in a nutshell, if a value of sigma exceeds a certain type of boundary condition, it'll diverge to 0. End of story. Yes. In the end, it is very useful, these Pauli matrices, in order to contemplate them. But there also are other things to contemplate. Like, for instance, staying on the topic of vector fields, what we are going to need to be doing is using these types of things that are called Hilbert spaces. Hilbert spaces, what they are Hilbert spaces basically are infinite dimensional spaces, which have an infinite amount of diverging vector fields, diverging, converging, etc. Ultimately, in a nutshell, they're an imaginary space. Of course, now, they can also be plugged into complex planes, but not all solutions to them. An example of a Hilbert space could be represented by Pauli matrices, but not always. Because, they can be a bit complicated at sometimes, so... Usually you can't really find the conjugate of these spaces. Now, one really good way to find out the eigenvector values of these would be to plug in this thing that's called HC in these equations, otherwise known as the Hermitian conjugates. Hermitian conjugate, you'll see it everywhere in quantum mechanics, from things like, you can see it in the field equations as explained in the Einstein field equations. You can see them in Paul Lewis de Broglie equations. You can see in the Dirac notation. You can see it everywhere in quantum mechanics. It's almost as popular in quantum mechanics as the Heisenberg uncertainty principle, which is quite incredible. Now staying on the topic of Heisenberg uncertainty principle, in case you guys don't know what it is, Heisenberg uncertainty principle is, in a nutshell, Heisenberg uncertainty principle would be, if you have uncertainty in your position, multiply it by the uncertainty in your momentum, which then is going to be equal to the Planck constant, because, well, Planck's constant is going to be a certain type of bound state boundary condition, which then is going to be a finite state of a certain type of momentum operator of the wave function. And then that's going to be over, well, putting downstairs, as many physicists usually say, 2 pi. Well, wait, is it 2 pi or 4 pi? Oh, wait. Yeah, it is 4 pi, actually. No, it's 2 pi, actually. Sorry. Anyway, so ultimately, Hermitian conjugates, one of the most widely used versions of it would be in the equations of, ultimately, they usually are used in the equations of the Standard Model. Now, Standard Model particle physics, they are very, very, very complicated. Usually they require many years of deciphering. I know, just like you know, I'm not going to tell you all the equations in this video, or else this video would be hours long. Because, well, for one, I would not only have to tell you it, but also I would have to explain all of those individual things. But I can give you a good representation of it in a simplified form. So ultimately, a simplified form would be called something is known as a quantum Lagrangian. Quantum Lagrangians, they are very useful in many, many fields. Like, for instance, in baryon physics, as explained in Feynman diagrams. They also are very, very useful in explaining the Standard Model as well, and also for looking at minimal potential energies in liminal spaces. Not superliminal, as you usually can see in some weird games that they may play. So some examples of them would be L, which means Lagrangian energy, which then is going to be equal to the sum of -4. -4 means the spin state of the momentum operator, which then is going to be multiplied by F mv multiplied by F to the power of mv. Now, just like the last one was sub mv, so sorry about that. But ultimately, what this means is that it's representing all the forces. It's representing the 4 forces of nature, the 4 types of scalar, not scalar, scalar bosons, such as the W, Y, and Z bosons, and also many others. Then, of course, there are other bosons like the Higgs boson, which give particles their mass, which then that's going to be added on to I, which then there's going to be another phi, which is going to be the wave function, which then is going to be multiplied by psi, and then that's going to be plus hc. Hc, of course, means Hermitian conjugate. They might be wondering, well, what is a Hermitian conjugate? Ultimately, it is defining the particle's values, the physical matter, the physical properties of the particles, which then that's going to be added on to psi sub I multiplied by y sub ij, which then is going to be multiplied by psi sub j, multiplied by phi plus hc. Hc, of course, again means Hermitian conjugate. Psi, as we all know, means wave function. Sub I means the imaginary component. Now, the reason why is because, well, imaginary components can be used in quantum mechanics as long as the sum of all of the vectors or anything that you're doing. If you're doing integrals, it better not have a sum of I. If it has a sum of I, you're doing something wrong. If it diverges to infinity, you're doing something wrong. If it is a non-linear space, you're doing something wrong. And then that's going to be multiplied by another value of psi, which then, of course, is going to be the wave function, which then is going to be multiplied by phi, which is the standard derivation, plus hc, of course, as we know, means Hermitian conjugates. Thus means the physical components of a particle in the standard model of particle physics, which then is going to be plus d, well, the finite value of, thank you, Preston, the finite value of d psi squared m minus v, which then is going to be the finite value, which then is going to be the time-independent value of psi, phi. Phi meaning the standard derivation, the finite value meaning the bound state boundary conditions of it, the d meaning the derivative, the phi meaning, phi meaning the standard derivation, squaring it means it simply does that, it's just a constant, v meaning particles' positions, and m meaning the mass of the particles. Now, so there is a lot of intuition behind this, and it gets a lot more complicated as other than that really simplified model. Now, if you're lost at this point, you're not alone. Everyone has been lost at this point with these equations. But don't worry, there is a simpler way of doing it. But it just is a bit harder to explain. And if you want to go see the crazy equations, all you have to do is just search up standard model equations, and you'll see what I'm talking about, why I can't explain it in this one video. I'd have to be talking for hours on it. And I might not even be able to explain some of the parts of it. So, in the end, yeah. If you want a pure representation of it, if you want a example of it, if you want me to explain it, please ask in the comments, and I may make an exception, and I may actually give you an explanation of all of the madness that goes on behind it, since, well, there's a lot of madness that goes on behind it. And just so you know, don't be disappointed if I can't explain all of it, okay? But I might be able to explain most of it. Alright, well, honestly, this has been a nice ride of quantum mechanics, as we've explained many different things like Brown-Kent notation and the intuition behind it. Hope you guys have liked this video, and hopefully I will see you soon.